Hello and welcome to Lapping Analytics. My name is Jimmy Lapping. I'm a psychologist and statistician with an interest in, among other, statistical methods for social and health science research and also AI applications in this context. In the previous video, I explained how you can use ChatGPT to perform all kinds of non-parametric statistical procedures. And in this video, I wanted to expand a little bit on that previous video. So if you're interested in this topic, here you find the link of that previous video that I just mentioned. What I did there is basically use a complete language prompt to ask ChatGPT to give some non-parametric statistics outcomes, point estimates and interval estimates. The only numbers in that language prompt was the data. So the question is, what happens if instead of numerical data, I use text? Because that's also possible, right? Because not all data that we use for statistics is numerical data, even if some people think that statistics is only about numerical data. So what would that look like? So I've taken exactly the same language prompt that I used in the previous video, but I have just very slightly tweaked it to deal with ordinal text data. What do we mean by ordinal text data? Well, here we see an example. Suppose you are a medical student who is practicing clinical skills, and as part of that practice you undergo a number of what we call stations, practice stations, where you, for example, see a simulated patient, and you need to ask questions about the health of that patient, simulated patient, usually an actor. Maybe perform a physical exam or a mental exam to explore a little bit what's going on, engage in clinical reasoning, etc. So there is a bunch of skills that you can assess in such stations, and there are different scales or orders to assess that performance. And if we take one of them, which is fairly common, is that, for instance, we say, okay, the best performance we call an excellent performance. Then there is a range of performances which we could classify as satisfactory, meaning that in a real situation this would likely yield a satisfactory outcome. Then there is borderline, which is basically, it's like in soccer, for instance, more like a yellow card. Like, okay, there are some minor lapses, some small mistakes, errors, but not such that they could have grave consequences for the health of a patient. And then there are also performances which are outright insufficient, which would probably lead to incorrect decisions, to maybe like adverse health outcomes for the patient. So you see, this is an example of an ordinal assessment, because there are 4 ordinal categories: insufficient, borderline, satisfactory, and excellent, from worst to best. So they can be ranked in a clear order. But you cannot say that the difference between borderline and insufficient is the same as the difference between satisfactory and borderline, or is the same as the difference between excellent and satisfactory. In fact, there is, as you see here, a wide range of performances that could be classified as insufficient, and there is also a fairly wide range of performances that could be classified as satisfactory. So these are not some kind of like 4 points which are equally distant to the next adjacent points. No? So there are ordered categories, but you cannot, for instance, say that the difference between borderline and excellent is twice the difference between excellent and satisfactory, for instance. That you cannot say. So it's ordinal data, not interval data. So, what can we do about that? So I actually used the, as I said, almost the same prompt as I used in my previous video, the link of which I provided earlier in this video. So what I see here is, okay, so students in two randomly created groups, henceforth called the control group and the experimental group, have their clinical performance on a short station rated as either excellent, best performance, satisfactory, second best performance, borderline, second worst performance, or insufficient, worst performance. The ratings for the control group are insufficient, insufficient, borderline, 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 excellent. So there are 7 um, control ratings, and for the experimental group also 7 ratings: borderline, satisfactory, 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 excellent, excellent, excellent. Important is the line: these ratings can be considered independent observations, so it's not some kind of, for instance, crossover design where you have the same people taking part in first one condition and then the other, and the order you could randomize. No, that's not the case here. No repeated measurements. It's not like twins or pairs of students that train together. We assume, okay, these are 14 different students that prepared for the station, and we treat them as independent observations. And then the prompt is compare each value of the experimental group with each value of the control group. Each comparison should be calculated as the difference experimental minus control, and the following questions should be answered. So what we have here is, first of all, a bit of context, right? So students in blah 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 all the way until what is the order of categories. That's the context, and which includes in this case the type of design that was used, experimental design with 2 randomized groups. Ordinal rating, because these are ordered categories. Data, which is, this is interpretable given that in the context piece we have defined in a clear manner the 4 ordered categories, so it's clear which is best, which is second best, which is second worst, and which is worst. So, and then given the context and the data, the order that we give to ChatGPT is to compare each value, or you could also say here each rating of the experimental group with each rating of the control group, and each comparison should be calculated as the difference experimental minus control, and the following questions should be answered. So first of all, the 5 questions. These questions are exactly the same as I had in my previous video. So total sample size, number of comparisons, how many comparisons yield a positive difference, meaning experimental larger than control, and how many comparisons yield a negative difference, and how many comparisons yield no difference. So look at these questions and you see that we are not interested in the absolute difference. We don't, for instance, ask questions here: how many comparisons yield in 1 category difference, 2 categories difference, etc. No, we just want to know how many comparisons yield a favorable outcome for experimental, meaning experimental better, how many comparisons yield a favorable outcome for the control group, meaning control better, and how many yield no difference, meaning comparisons where the rating from the experimental group yields the same, is the same as the rating in the control group. So then we continue, because based on questions 1 to 5 we can calculate the relative effect, and the numerator of that is the sum of the answer to the questions 3 and half of the sum of the answer to question 5, because it's the positive differences, and half of the ties. The ties are equally split over positive and negative. And the denominator of the relative effect is the answer to question 2, the number of comparisons. So then question 6, what's the value of the relative equivalence? From that, in question 7 and 8, we calculate the number of successes and failures based on the total sample size, so not the number of comparisons, because in this case there are 7 cases in each group. So that means 7 times 7 is 49 comparisons, but the sample size is 14. And we calculate, we basically recalibrate the number of successes and failures to the from the number of comparisons to the total sample size. Why do we do that? Well, among others, because we want to calculate the so-called generalized relative effect, which follows a beta distribution, and the default prior for that is a 1-1 prior, meaning we add one success and one failure. If you want to know the rationale behind that, I explained that briefly in that previous video, that this video is a follow-up for. And I also can provide the link to the article in which this statistical procedure was introduced. It's a publication from last year. And then, well, based on that information, you get questions 9 to 13 about the central tendency of the generalized relative effect, questions 9 and 10, and some credible intervals, which are not the same as, but similar to confidence intervals for that you know in the frequentist school of statistics. They are not the same. They are philosophically and mathematically slightly different, but they have the 95% credible interval will, with a default prior, normally give a be very similar to the 95% confidence interval in the frequentist school of thought. Okay, so this is what ChatGPT, which is by the way the free version of ChatGPT, so I'm not using any professional version. This is the last freely available version of ChatGPT, the last meaning the most recent free version of ChatGPT. So it says, let's go step by step and keep everything explicit. It sees here ordinal coding. Yeah? So it has correctly identified the natural order, meaning that insufficient is smaller than borderline. Borderline is smaller than satisfactory, and satisfactory is smaller than excellent. So it correctly identifies that excellent is best and insufficient is worst. And yeah, you also see you provided control group n equals 7, so the sample size of 7 with the data, experimental group as well, 7 as a sample size, plus the data. All observations are independent. That's what we provided as information. And the pairwise comparisons, that's the order below here. Each experimental rating is compared with each control rating. So this is a correct summary of the information that we fed to ChatGPT. And then the questions are easily answered. Question 1, total sample size 14. Question 2, number of comparisons. Well, that's 49, 7 times 7, as I explained before. Question 3, 38 positive differences. Question 4, 4 negative differences. And question 5, 7 ties. If you want to know the rationale behind these numbers, again, in the previous video I explained these very briefly, but these answers are correct. And question 6, so that is the relative effect, which is the number of positive differences, meaning in favor of the experimental group, plus half the ties, because remember the ties are equally divided over positive and negative. So that means we have a relative effect estimate of 0.84694. Number of successes, what do we do? Take that relative effect estimate and multiply it not with the number of comparisons, because then we would get back to the 41.5 in the numerator. We multiply by 14 because that is the total sample size. Remember, we want to calculate the number of successes and failures using the total sample size, which is 14. So nearly 12 of that is success and just over 2 of that is failure. I also explained that in the previous video, but if you wonder, hey, these are not whole numbers, is that even possible? Yes, it is possible. In the Bayesian proportion test, you can have decimal numbers as successes and failures. That is no problem at all. In fact, it is very common. And what we do then is, well, that piece of information that we gave, okay, the generalized relative effect is basically a Bayesian statistic that we use. We add a default 1-1 prior. Just if you have no specific information, prior information based on solid theory or previous research, then usually for beta procedures, a 1-1 prior is a good starting point. And so what we get is we have the data, which is 11.85 something and 2.14 and a bit, and then we add the prior 1-1. So what do we get as successes? 12.857 something, and as failures 3.14 and a bit. That is the posterior distribution, the posterior beta distribution. And with that information, we have all that we need to answer the remaining questions. Question 9, the posterior mean. Question 10, the posterior median, which is the 50th percentile of the posterior distribution. And then question 11 has the 95% credible interval, which is of these intervals closest to the 95% confidence interval, slightly smaller, but not much. And 12 and 13 give the 90 and 89% credible interval. Again, for explanations around these credible intervals, I refer to the previous video which used this language prompt and including the full set of questions as well. As I explained in that previous video, it's important to, when you write a language prompt to practice statistics using AI tools like ChatGPT or DeepSeek, for instance, it's important that you test with some test data, that you test the accuracy of the prompt, the validity of the prompt, validity of the outcomes in a program like R or Jamovi or Stata program that you work with, and that you know gives the correct answers for, well, what you want to, what you're interested in, which is what I did as well when I developed this language prompt. I also ran the whole numerical analysis with code in R, and well, got the same outcomes. So that's important because, well, I've also shown in another video that it's important to check, because sometimes sometimes ChatGPT and other programs alike can make mistakes, and you also see it. When you open ChatGPT, usually in the footnote of the program, it makes a remark: ChatGPT can make mistakes. So it's important to test at least your language prompt with another statistics program. Once you've done that, it should probably be okay. Okay, I hope this was useful. I thought this I should add this video with ordinal text data in a future video at some point on this channel. I will also talk about solutions for nominal text data, meaning text data that can be interpreted as distinguishable categories, qualitatively different categories, but there is no order, at least not a unidimensional order in terms of worst to best, or lowest to highest, for instance. But there are solutions for that as well. That's one of the reasons why I developed this approach called the generalized relative effect, but that is material that I will keep for a future video. Thank you for watching, thank you for listening, have a nice day, and maybe see you in a next video. Bye bye.